אפילו יותר. Thank you very much for the honor in presenting in this historical meeting. Our presentation expresses our thankfulness to the AB effect and to A and B for the profound insights which they offer into quantum theory. We begin with a very basic notion in quantum theory, which is superposition. Superposition lies at the basis of the theory, and at the same time it is subject to a very interesting censorship. You can never observe a superposition directly. You can only infer about its existence indirectly later. So if you take this case of interferometry,
Cannot arrange now anything, so you have to speak loud. In the
okay.
For you?
So I'm talking about the censorship on superposition. Superposition must be there. That's the essence of quantum theory. But there is a censorship that prohibits you ever from seeing it, from observing it directly. If we take this familiar example of an interferometer, the particle gives rise to an interference by virtue of its being superposed, that is taking both the right and the left path. You may, of course, make a measurement as a result of which you will ruin this interference, and it will be either on the left or on the right. And then, of course, there will be no interference. What about the possibility of making a more subtle and more indirect measurement, such as doing it on an entangled particle? So here we have an EPR source, the correlation between the two particles being the wedge path. And we have Alice and Bob. And if Alice does not make any measurement, then Bob's particle is superposed and apparently being capable of giving rise to interference, whereas Alice may choose to make a measurement as a result of which she may find it either on the right, the same will be with Bob, or on the left. And that seems to deny Bob's particle the capability of interfering with itself. But here is where the censorship comes and prohibits you to know what went on. That is, whatever Bob is doing, he will not be capable of knowing whether Alice chose to make a measurement and what kind of measurement she made. So it is this censorship that guards causality in this case and does not allow any signal. Just to make it familiar, clear, let's replace this with spin-half particles. So in this case, we have two Stern-Gerlach magnets, and that will be the interferometer. And the first one splits the particle into two. Then the other one is actually erasing the first measurement because it is aligned at the x direction oppositely. And then you have an eigenstate of z spin before and after, and that will be your interference. That will be the analog of what we had in the earlier example. And here again, whatever Alice and Bob are doing, no signal can be transmitted this way due to the same censorship. So here we have an EPR-Bohm source, so the correlation is a correlation in terms of spin, and we are assured that the censorship holds here as well. Things will be much more profound when the AB is implicated. Let's think about a current now, which is being superposed within such a large interferometer. So the current may be superposed, and then we can arrange it such that it will interfere, and then we will always get a click in what we call here C. Or we might make a measurement, break its superposition, such that it will be either on the right or on the left, as a result of which we might have clicks either in C or in D. And now the combination of EPR plus AB makes things much more intriguing. Here again we have our Alice and Bob. Now it is an EPR-Bohm source. And the question now the problem now cannot be as easily dismissed as in the last time. Alice may refrain from doing anything, as a result of which Bob's particle remains superposed. Now, it is because of it is being superposed that it may feel the AB effect, it may gather the phase around the solenoid. And then, of course, he's making a measurement. Now the current is not superposed. Either it is in that solenoid around which Bob's particle goes, or it is not there. So Bob is not concerned about his own interference, but rather of the interference of the two solenoids. And in this case, he must see E, D, and C clicking equally. Alice may, however, choose to make a measurement in which she has her particle not superposed, and now we understand that Bob's particle is not superposed either. Therefore, it is devoid of the possibility of sensing any AB effect, and then it should leave the superposition intact, and then we are going to see only clicks in C because there is an interference. So what concerns us now is that there is a physical difference between the two cases. We shall neglect this kind of phase. And what do we do now? Some people may dismiss the whole thing, say this is all too gedankenly for us. What you guys are actually asking is a Schrödinger cat. You want a macroscopic current be superposed and then give rise to interference. You can't get that. And of course, this is not the kind of answer that we shall take. Moreover, we can have something similar being practical. If we go two-dimensional, then we can make a flux be quantized and behave quantum mechanically, and now our question can be rephrased again in these terms. So we have again Alice and Bob, and now we have a flux on an electron being treated both quantum mechanically. And here again, Alice may refrain from doing any measurement, and then Bob's particle is superposed. This way, now the fluxon cannot be superposed, because if by Bob's very sensing or not sensing, gathering or not gathering the AB phase, then the fluxon must be inside his interferometer or outside of it, and as a result, interference is lost. And the same for this case. Alice may, however, again, make a measurement, in which case this particle is now not going around the fluxon or here, and then interference remains intact. So here, the question is now whether causality may not be compromised. What we did here is actually treat the fluxon and the electron on the same footing, both of them being quantum mechanical, and this is what makes now the dual effect emerge very naturally by placing them on equal footing. Because what we have here comes to our rescue, the dual effect that says the following. Alice indeed make a measurement. We take the second case in which the particle goes outside, and then, of course, the interference of the fluxon will remain intact. She may get it going on this side, which means that Bob's electron will go inside, pass through the fluxon's interference, and then it will leave the interference. It will interfere, but the interference will be shifted. So here we have something very peculiar. Apparently, a signal was sent. Apparently, what Alice did was to tell Bob's electron, you're no longer superposed. You cannot have an AB effect. In half of the cases, you are going to go through the fluxon, but then it is the fluxon who must now, whose interference, which remains intact, must be shifted. And this is, I find it very intriguing because both AB and AC are playing together in a way that masks any possibility for Bob to know what was going on, because they give exactly the same statistics. So this time it is requiring the phase in accordance with Bob's particle's location. So whatever she is doing does not make any difference. Although, once again, I find it so intriguing that both effects play the same role, because both the electron and the fluxon are both quantum mechanical. So it emerged just by putting them on equal footing. Shall we take a more intriguing kind of a macroscopic cat-like state? How about if the fluxon goes either clockwise or anti-clockwise? And here again, we are on a convenient ground of talking about experiments that have been carried out, similar to what we are looking for. Because we are now in 2 dimensions, then the solenoid turns into a squid, and then it is in a superposition of either going clockwise or anti-clockwise. Notice that this Josephson junction by tunneling takes care that the generacy will be removed and we will have only the ground state. And now we can rephrase our question. Here is how the experiment looks like. You have the penetrating flux, and then you have the superposition of the current taking either the clockwise or anti-clockwise. And here is Bob's particle. And Bob's particle can now be entangled with a flux in either way. We can say, for example, that if the flux goes clockwise, then Bob's particle will emerge from here, and vice versa for the other direction. We may worry about the induced magnetic field, so for this purpose, let's put a superconducting layer that will take care of that. And then we can again rephrase our question. Alice does nothing, and then Bob's particle is superposed. But by being superposed, now we can observe what kind of shift it gets, such that the current is now forced to be either clockwise or anti-clockwise, or Alice is making measurement by which she denies Bob's particle the capability of going around the flux, and then it will leave the superposition intact. This is a topological effect, and it would be ridiculous to believe that just by some remote electron doing part of the way it can make any difference, so the superposition in this case remains. What can we do now? AC will not help us because the superposition now is not between two solenoids that give rise to interference, but it's the same solenoid within which the current may go either clockwise or anti-clockwise. Let's first dispense with the easy case. Suppose that the electron goes near and fast, such that it can be felt. Then there is this work that shows that what we will have here will be some back reaction, such that Bob's particle will change the flux, the state of the flux, even when it is not interfering, just by going near it. And in this case, Bob cannot distinguish between the two choices of Alice, and no paradox ensues. But what if we take care that this is not the case? And the interference time is very long, and the interaction is very weak. Along come to our rescue another obscure paper by an obscure group many years ago, which claimed something completely bizarre, and they say the following. You took care of this Josephson junction remaining the degeneracy, and then you made sure that the particle goes very slowly. Guess what you prepared the stage for the following thing. Imagine this electron being in a superposition within these two boxes with this pipeline ensuring this kind of degeneracy removed. And then you want to make a measurement. So you have a measuring charge here. And by its very repulsion, you can tell whether the electron was in the left box or in the right box. By the way, it repels. Nice. This is strong measurement. But what if you take care that the interaction is adiabatic, very slow? Then you will have this incredible thing of the electron remaining superposed and the measuring charge taking the incredible path between them, telling you actually that it has felt half an electron on both sides, repelling it equally. Guess what? This is just what we did here. We just prepared the stage for the measurement being protective. The flux remains superposed because of what we did, because of the two things, both the Josephson junction removing the degeneracy and the interaction being very slow. Even if Alice does nothing, Bob's particle remains unentangled with the flux, measuring the flux's expectation value, which is incredibly 0. No AB phase, no paradox. So in conclusion, AB bears on several fundamental quantum mechanical issues, causality, non-locality, adiabaticity being only a few of them. In one case in which there was an interference between fluxes in two solenoids, then the very fact that we treated both of them on equal footing as quantum mechanical objects, then the AB and AC emerged naturally as complementary, as dual effects, and electrons and fluxons, both of them interact topologically. In the case of fluxon superposition, in which you had one solenoid, causality was protected either by the easier case of back reaction where the interaction was strong, and when you took care to prevent that, then you brought the measurement becoming protective and preserving the expectation value. That both the AC and protective measurement were discovered by the same man, I believe, is of little surprise. Very likely, Yakir, faithful to his peculiar way of time and causality, prepared the remedy long before the infliction. Thank you very much.